This is part 3 of the lecture series on analyzing test questions on nuclear physics. The emphasis in this third part of the series is questions related to nuclear fission and nuclear fusion. Question number 1. Consider the nuclear reaction hydrogen isotope or deuterium plus beryllium isotope beryllium-9 produces an unknown nuclide labeled here as capital X and an emission of an alpha particle or helium nucleus. Question letter A, what are the values of Z or the atomic number of the unknown nuclide X and its mass number capital A? For letter B, how much energy is liberated in this nuclear reaction? So we are going to use the following atomic masses. For deuterium, it is 2.014102 atomic mass unit. For beryllium, it's 9.012183 atomic mass unit. And for alpha particle, it is 4.002603 atomic mass unit. For our first question, or the basis in answering the questions, is simply for us to find the energy released in this nuclear reaction. We also call it the reaction energy. And this can be calculated by getting the difference between the total mass of the initial nuclei, such as deuterium and beryllium, and then the total mass of the final nuclei, which is the nuclide X and the alpha particle or the helium nucleus. And then, once we get the difference, delta M, we just multiply it by the constant 500 or 931.5 million electron volts. That's actually the square of the speed of light, c. Alright, so for our first question, determining the atomic number of the unknown nuclide X. So what we do is, we just add, alright, we just add the atomic number of deuterium, which is 1, plus the atomic number of beryllium, which is 4, and then deduct the atomic number of an alpha particle, which is 2. So what we get is a Z value of 3. And that element or nucleus, which has an atomic number of 3, is actually the the nucleus lithium, whose atomic mass number is 7. Right? We can verify that by also getting the mass number. Simply we just add the mass numbers of the reactant elements, meaning 2 for deuterium plus 9 for beryllium, and then deduct the mass number of alpha nucleus, which is 4. So 2 plus 9 minus 4, we get 7. So the unknown nuclide, okay, with an atomic number of 3 and a mass number 7 is actually the element lithium, whose atomic mass is in fact 7.016003 atomic mass unit. Alright, so for our question letter B, okay, again, we get the total mass of the initial elements or nuclides, such as deuterium and that of beryllium. So this atomic masses 2.014102 will just be added to that of beryllium, which is 9.012183, for a total of 11.026285 atomic mass unit. Likewise, alright, for the resulting nuclides in the products, For the nuclide, what do you call this? Lithium, its atomic mass is 7.016003 atomic mass unit, and for an alpha particle, it is 4.002603 for a total of 11.018606. And if you're going to get the mass difference, we will get positive 0.007679 atomic mass unit. In other words, the total mass of our initial nuclides is greater than those, or than the combined masses of the resulting nuclides, for a difference of positive 0.007679 atomic mass unit. All right, so a nuclear reaction which has a mass difference between the initial and the final nuclides, when it is positive, it is given the term exoergic reaction. When it is negative, the term used is endoergic reaction. All right, so using this data for our delta M, we now convert this to its equivalent in million electron volts. And that is simply multiplying this delta M by 931.5 million electron volts for every atomic mass unit. And our result is we get the equivalent energy, which is positive 7.15 million electron volts. And this amount of energy has been liberated. Actually, this is in the form of kinetic energy of the two nuclides, meaning the lithium nuclide and the alpha particle, having a total kinetic energy amounting to 7.15 million electron volts. Before I proceed to the next question, let us first talk about a decay process in which an unstable nucleus splits into two fragments of comparable mass. And this is usually known as the fission reaction. Okay, let's look at two typical examples of what we call an induced fission reaction. When you say induced fission reaction, this is a kind of fission where the neutron is used. Okay, it is used to bombard the unstable nucleus. Okay, for fission reaction to occur. Example is when uranium-235 is bombarded with a neutron. In other words, when a uranium-235 isotope absorbs a slow-moving neutron, then it splits into two fragments, such as barium and krypton. But before that happens, the fact is, uranium-235, upon capturing one neutron, first it becomes an excited isotope of uranium-236, as shown in this equation. Alright, so uranium-236, in its what we call unstable, very unstable state, alright, but instantaneously, this uranium-236 in its unstable state will instantaneously splits into barium nuclide with a mass number of 144 and krypton with a mass number of 89, and at the same time 3 neutrons are also released. So this is one typical example of an induced fission reaction or fission reaction. The other possibility is for the same unstable nucleus uranium-235 upon capturing one neutron, all right, and upon becoming a very unstable uranium-236 in its very excited state, okay, will also produce xenon, whose mass number is 140, plus strontium with a mass number of 94, but only 2 neutrons will be released. So these are examples of what we call induced fission reactions, where a neutron is used to bombard the heavy unstable uranium-235. Okay, uranium-235 can easily be split or can easily undergo fission when the neutron is considered to be slow moving. Okay, another isotope, the more commonly available isotope of uranium, which is uranium-238, okay, cannot be split if the neutrons are slow moving. Right? When you say slow moving, the neutron should have a kinetic energy of 1 kilo electron volts. But for uranium-238, it requires a neutron that is moving at a very high speed, such as 1 million electron volts. So normally, under ordinary condition, we say that uranium-235 is more fissionable compared to uranium-238. Okay, even if uranium-235 is less abundant in nature, it's only 0.3%. The amount of uranium-235 found in uranium ores, okay, in uranium minerals, okay, a certain uranium mineral contains only 0.3% of uranium-235. Most of the uranium isotopes that are naturally occurring are uranium-238. So, since it is uranium-235 that is used in most nuclear reactors, all right, the uranium-238 mineral or uranium mineral ores have to be enriched, okay, to be enriched with uranium-235 so that a considerable amount of nuclear fissions can be induced, okay, for the desired amount of um, energy needed by a nuclear power plant. All right. It is found out that every fission reaction, the average amount of energy that is released amounts to 200 million electron volts. So this is relatively a very uh, high amount of energy as compared to ordinary nuclear decay reactions. This one, fission reactions, okay, always involves the release of very high amount of energy being released. Why is this so? Well, this has something to do with uh, nucleons, all right, or nuclides with very high mass numbers, such as those elements with atomic mass of or mass number equal to 240. All right, the binding energy of these elements can reach up to 8.5 million electron volts per nucleon. All right, uh, but the lighter nuclides, those with mass number of 120, okay, only has about or has in fact much higher binding energy per nucleon, amounting to 8.5. Okay, So what you are seeing is elements whose mass numbers are way above, such as A equals 240. They are not so binded. All right, their binding energy is relatively low as compared to those light nuclides having a mass number of 120. All right, so uh, uranium-235, for example, belongs to that category of having low binding energy, so that during the nuclear fission reaction, okay, the delta E, okay, between the typical amount of binding energy per nucleon and uh, those for lighter nuclides, all right, we will be able to more or less get an average of 0.9 million electron volts per nucleon. And in the case of uranium-235, this amount of the energy difference, binding energy difference, which is 0.9, when multiplied to the number of nucleon of uranium-235, that amounts to approximately close to 200 million electron volts. So this is how we are able to approximate the amount of energy released during a typical induced fission reaction of a heavy unstable element such as uranium-235. Remember that when we discuss stability during the second part of our or first part of our lecture series, emphasize the tutorial video or video tutorial that stability is attained by a nuclide if the number of neutrons or the ratio of the number of neutrons over the number of protons is equal approximately to 1. Okay, this is true for light nuclides. Okay, light nuclides in the category of nuclides having a mass number 120 and below. Okay, the neutron to proton ratio is almost equal to 1. Whereas for those heavy nuclides, including uranium, the required ratio for neutron to proton is at least 1.6. Okay, so the result of the nuclear fission reactions, whereby uh, the the nuclide uranium-236 is split into uh, fragments of uh, nuclides such as barium and krypton, or xenon and strontium, okay, which are by themselves radioactive. All right. In other words, when they are released as the byproducts, they themselves, okay, undergo nuclear transformation, okay, to achieve stability. All right. So a typical example is the case of xenon. When xenon is a byproduct in a typical uranium-235 fission reaction, xenon by itself is unstable. So, okay, to achieve stability, it has to emit series of beta minus particles. For example, right, when it emits a beta particle, it becomes this nuclide CS, cesium, isotope 140, all right? And then again, this nuclide cesium will again emit a beta minus particle, okay, and it becomes an isotope barium 140, which by itself is also a beta minus emitter, Okay, so upon emitting beta minus particle, it becomes another element labeled as La, whose mass number is 140, and finally it becomes the stable element Ce, right? Whose mass number is 140. So that is a typical example of the fragment nuclides that are produced during fission reactions of uranium-235, which actually becomes uranium-236, okay, at its very high uh, state before becoming barium or krypton, or possibly xenon and strontium. So all these things happen because of uh, the element's desire to become more stable. So the very objective of these elements, unstable elements, is to achieve nuclear stability, right? Nuclear stability can be achieved, okay, by emitting radioactive particles such as alpha or beta. And together sometimes, upon emitting beta particles, okay, an electromagnetic radiation known as gamma radiation may also be emitted. We'll now move on to question number 2. Given the polynuclear fission reaction, when plutonium isotope 239 captures a neutron, it splits into the following nuclides: strontium 96 plus an unknown nuclide labeled here as X, and releases 4 neutrons. Given the following atomic masses, for neutron, which is 1.008665 atomic mass unit, for strontium 96, it is 95.92175 atomic mass unit. For plutonium, okay, the atomic mass is 239.052157 atomic mass unit, and for this unknown nuclide, the atomic mass is 139.910581 atomic mass unit. First question, letter A, determine the atomic mass, capital A, and the atomic number, capital Z, for the unknown nucleus X. You are to identify what element it is. Question letter B, find the energy in million electron volts released by this fission reaction. So, just like in our example number 1, we first get the mass number A of the unknown nuclide, and that is done by uh, getting the difference of the mass numbers for plutonium 239, then for neutron it's 1, so a total of 240. Okay, 240 as the mass number of our initial nuclides. Then minus 100. Why 100? Because for strontium, the mass number is 96. For the 4 neutrons, it's 4, a total of 100 nucleons. So 240 minus 100 nucleons, we get 140 as the mass number of the unknown nuclide X. Alright. Now, for the number of proton, or atomic numbers, capital Z, again, we add 94. That's the number of protons of plutonium. Okay, a neutron has 0 charge. And then the combined number of protons of strontium, which is 38, but neutron has zero charge. So we subtract 94 minus 38 gives us 56. And 56 is the number of proton or atomic number of the element X. And upon checking in the periodic table, this element with an atomic number 56 and a mass number 140 is in fact barium. That answers our question letter A. So for question letter B, find the energy released during this reaction. We first determine the mass difference, delta M. Alright, so the mass of the initial nuclides or reactants, which is the combined mass of plutonium 239.052157, okay, plus the atomic mass of a neutron, all right, which is 1.008665 U. So the mass of the reactants or initial nuclides therefore is 240.06082 atomic mass unit. For the final nuclides, the mass of the products, all right? So we add the mass of strontium, atomic mass of strontium, okay, 95.92175, and the atomic mass of what? What is this? 4.0. This is the atomic mass of the 4 neutrons, all right? So each neutron has a mass of 1.008665 multiplied by 4, since there are 4 neutrons, okay? That gives us a total of 4.03466 AMU. And lastly, the atomic mass of strontium, which is, of the unknown nuclide, X, which you have identified to be barium. Okay, the atomic mass of barium, which is 139.910551. All right. So our total, what you call this, mass of the final products is 239.866991 AMU. So that when you subtract, okay, the mass of the initial nuclides minus the total mass of the final nuclides, our delta M or mass difference is equal to positive 0.193831 atomic mass unit. Alright, we need this to be able to get the energy, okay, released during the reaction. So we simply multiply that delta M by the constant 931.5 million electron volts for every AMU. And the equivalent energy in MeV is 181 million electron volts. This is the answer to letter B, the energy that is released during this nuclear fission reaction involving plutonium 239 bombarded by a single neutron. All right, so before we proceed to question number 3, let's first talk about a nuclear reactor. We have here a schematic diagram of a nuclear reactor. So what is a nuclear reactor? It's just a system in which a controlled nuclear chain reaction is used to liberate energy. All right. So in here, which represents what we call the primary loop, we have there the reactor core. All right, the reactor core uh, that is where the fuel, which is uranium, of course, uranium-235, will undergo the fission reaction. Okay, so inside this reactor core is what we call a moderator, right? A moderator, it's either water or graphite. It is the material that surrounds the uranium material, which the role of the moderator is to slow down the neutrons, right? So the neutrons that will be released during each fission reaction, remember earlier, okay, in every fission reaction, okay, there are what we call a number of neutrons that are released. Free neutrons are released, all right, which can possibly also induce the next fission reaction, all right? So as more neutrons are being released inside the reactor, more and more fission reactions will happen, okay? And this series of nuclear fission reactions happening, okay, in such a short period of time, okay, producing tremendous amount of energy is what we call a chain reaction, all right? So in a typical nuclear reactor, this chain reaction has to be controlled. Okay, we have to regulate, in other words, as to how many neutrons, okay, will be released for every nuclear fission, so that the desired number of neutrons will again induce the next nuclear fission, and so on. This is done by having what we call control rods, right? Control rods made of either boron or cadmium. So from the word control rods, they have the ability to control the rate of the reaction. Okay? If the control rods, represented here as these uh, long rods, all right, when these are inserted into the reactor core, all right, then they have the ability to what we call they have the ability to capture the neutrons, all right, the neutrons that are not needed to further continue the nuclear fission reaction. So the farther the control rods are inserted into the nuclear reactor core, the more neutrons will be captured. All right. So uh, scientists or nuclear engineers, physicists know how they are able to control, right, the fission reaction with the use of these control rods. Okay, now uh, the water that gets uh, or that increases the temperature, okay, this water that is heated as a result of the energy that is released during the nuclear fission reactions, okay, this water, okay, will be converted into steam, all right, and it is the steam or highly vaporized water that will what we call drive a turbine, right? The steam that is highly pressurized has the ability to make the turbine rotate, And in the process, this turbine, which is connected to an electrical generator, okay, the generator, as we probably know when we discuss, okay, electromagnetic induction in your previous physics lessons, okay, it is the generator that generates the power or the EMF that we need in order to come up with useful form of energy, which is electrical energy. All right. So it looks like that the role of the nuclear fission reaction is simply to provide the energy or the thermal energy. Okay, the thermal energy that is contained in the form of internal energy of the heated or vaporized water. In other words, the internal energy of the steam, all right, is the one that is providing the needed mechanical energy, okay, to make this turbine move so that the electrical generator can convert mechanical energy into electrical energy. All right, so the nuclear power derived from the nuclear fission reaction, in a way, can be considered as our fuel, okay, as differentiated from other uh, power reactors such as the coal uh, power, okay, power plant, where coal is burned, okay, to produce the same heated or vaporized water, okay, exactly the same process, okay, as to how the electrical energy is produced. The only difference between a nuclear power plant and a coal power plant is what is the raw material used as the fuel. So for a nuclear power plant, we make use of uranium, specifically uranium-235 as our fuel, okay, to produce heat, all right, to produce heat that is needed to vaporize the water so that the steam that is produced can generate electricity. Right? So in the next problem or question, we're going to see how much energy is generated in a typical nuclear power plant. All right, now question number 3. What mass of uranium-235 has to undergo fission each day to provide 3,000 megawatts of thermal power? So our solution is, of course, we will assume that the fission liberates about 200 million electron volts per nucleus or per atom. This was mentioned earlier. 200 million electron volts per fission reaction. So in each second, that would mean, okay, producing energy equivalent to 3,000 million joules. Okay, each fission provides 200 million electron volts, which is, when converted to joules, okay, 200 million electron volts, we just multiply it by the equivalent of 1 million electron volt in joules, which is 1.6 times 10 to the negative 13 joules. So we will get this equivalent energy, all right, 200 million electron volts is just equivalent to 3.2 times 10 to the negative 11 joules. We can now determine the number of fissions needed, okay, in each second. So we simply divide 3000 times 10 to the 6 joules. That is the equivalent of 3000 megawatts of power. When converted to megajoules, that's 3000 times 10 to the 6 joules, divided by this amount of energy per fission reaction, 3.2 times 10 to the negative 11 joules. So we will get this number of fissions, okay, in each second. In other words, we need 9.4 times 10 to the 19, okay, uranium-235 nuclei, okay, to produce this amount of thermal power, 3000 megawatts. All right, that is in 1 second. So what we want is in 1 day. All right, so before we will be able to get that amount of uranium to be used, okay, in 1 day, we first convert the atomic mass of uranium 235 by multiplying it by this equivalent or conversion factor in 1 atomic mass unit. We have 1.67 times 10 to the negative 27 kilogram. All right, so we will get 3.9 times 10 to the negative 25 kilogram as the mass equivalent in kilogram of uranium-235. All right, and then we will now get the mass of uranium-235 needed each second. That is 3.9 times 10 to the negative 25 kilogram multiplied by 9.4 raised to the 19th, all right, fissions. So we will get this 3.7 times 10 to the negative 5 kilogram of uranium, all right, or 37 micrograms. All right, this is in 1 second, 37 micrograms. But we are talking about a period of 1 day. So in 1 day, we know that there are 86,400 seconds. So therefore, the total consumption of uranium-235 would be, multiply that value, 3.7 times 10 to the negative 5 kilogram per second, by 86,400 seconds, for a total of 3.2 kilograms of uranium fuel. That's in 1 day. Okay? So for comparison, okay, a typical 1,000 megawatts coal-fired power plant, all right, can burn up to 10,600 tons or about 10 million kilograms of coal per day. Can you see the difference? Okay. In order to produce a power output of 1,000 megawatts using coal as our fuel, we need 10 million kilograms of coal per day as compared to using uranium-235, which only requires 3.2 kilograms of uranium per day. So you can just imagine the what do you call this? The difference in the amount of fuel, okay, that you can save, okay, if we decide to use nuclear power plants as our source of energy. Our last question, question number 4. In the fusion reaction uh, shown here, you are to find the energy released, all right, expressed in million electron volts. So the nuclear fusion reaction equation goes like a hydrogen isotope known as deuterium, okay, fuses with another hydrogen isotope known as tritium or tritium, and produce these products: helium nucleus plus 1 neutron, of course accompanied by the release of energy E. So using the following atomic masses for deuterium, tritium, helium, and the neutron, we will find first the delta M, or the mass difference between the initial and the final nuclides. So for our initial nuclides, their total mass is 2.0141 plus 3.0161, a total of 5.0302 atomic mass unit. And for the final products or nuclides, okay, we have 4.0026 AMU, which is the mass of an alpha particle, and 1.0087 AMU for a neutron particle, for a total of 5.0113 atomic mass unit. Okay, so notice that there is a difference in the mass, combined mass of the initial nuclides with the combined mass of the final nuclides. So a difference amounting to 0.0189 atomic mass units. We then convert this to its equivalent in million electron volts by just multiplying that by 931.5 million electron volts per atomic mass unit. So we get the amount of energy released in this fusion reaction, which is 17.6 million electron volts. Right. So this is the answer to our question. Unfortunately, nuclear fusion reaction is not yet possible at this time. The reason is we cannot have a nuclear reactor that can sustain the tremendous or extremely high temperature needed for a typical fusion reaction to occur. Okay, but right in the sun's center or core, the nuclear fusion reaction, also known as thermonuclear reaction, is what produces the heat and light energy of our star, the sun. Okay, so it takes a while probably for us to be able to utilize the energy that is produced in a nuclear fusion reaction. Research is now going on to look into the possibility of having a nuclear fusion reaction without having an extremely high temperature. Okay, this is what they call cold fusion. But for now, that is still a distant possibility. So we just hope that in the near future, we will be able to utilize, all right, the energy coming from a fusion reaction, because, as they say, the energy that is harnessed in a fusion reaction, aside from its more, more amount of energy can be utilized compared to an ordinary fission reaction. And one thing more, it is environmentally clean, because there will be no what we call radioactive substances that will be produced in the process. Okay, so we will not be having what we call nuclear waste, just like what we have in typical nuclear fission reactions.